Good day everyone, welcome to this video. Without further ado, let's talk about optimizing constraints leveraging the Simplex Maximization Method with equality. Simplex Maximization Method with equality is a powerful tool for solving linear programming problems and maximizing objective functions subject to various constraints. In this presentation, we will explore the principles and applications of this method. As linear programming is a crucial leveraging simplex method, it involves maximizing or minimizing a linear objective function, subject or linear equality or inequality constraints. This mathematical technique has widespread applications with the various fields such as economics, engineering, and operational research. Simplex algorithm is an iterative procedure for solving linear programming problems. It systemically moves from one feasible solution to another, improving the objective function value at each step. By leveraging the simplex algorithm, we can efficiently optimize constraints with find the optimal solution for complex problems. Optimizing constraints can allow us effectively optimize constraints by identifying optimal values of decision variables. By systematically exploring the feasible region, we can maximize the objective function while satisfying all given constraints. This method can provide us a systematic approach to decision making and research, allocation, and planning. Feasible region, which represent the set of all feasible solutions that satisfy the given constraints in a linear programming problem. In leveraging the simplex maximization method, we can efficiently navigate this region to identify the optimal solution that maximizes the objective function while adhering the constraints. Equality constraints is how into linear programming problems adds an additional layer of complexity that provides systematic approach to handling these constraints and finding the optimal solution while ensuring that all equality constraints are satisfied. This enables us to effectively optimize the given constraints. And the ultimate goal for simplex maximization method with equality constraints is to identify the optimal solution that maximizes the objective function while satisfying all these given constraints, which the solution provides valuable insights, planning, and other decision-making processes. In the sensitivity analysis, it's a allow us to assess the impact of changes in the constraints coefficients, the objective functions coefficients on the optimal solution. This analysis provides valuable information for decision making in dynamic environments. For the application, the principles of optimizing constraints using the simplex maximization method with equality constraints can have diverse application across industries. From supply chain change management to financial planning, this method enables efficient resource allocation, production optimization, and strategic decision making. And it has also challenges and limitations. While the simplex maximization method is a powerful tool for optimizing constraints, it also inherent challenges and limitations because may include computational complexity and scalability issues or sensitivity to input data. By understanding these challenges, in essential for effectively applying the method of practice on these scenarios. In the future developments of maximization is to continue evolve the future algorithms and computational techniques in order to hold a promise for addressing the challenges associated with Simplex Maximization Method, where we can embrace advancement in optimization theory and technology will further enhance our ability to leverage this method for constraints optimization. Example word number one is a company manufactured two products, A and B. Each unit of product A requires 2 hours of work on machine 1 and 1 hour for machine 2. Each unit product B requires 1 hour of work on machine 1 and 2 hours of work in machine 2. Machine 1 is available for 8 hours a day and machine 2 is available for 8 hours a day as well. The profit on each unit of product is A is $3 and the profit of each unit of product B is $5. The company wants to determine the number of units of each product to produce the order to maximize profit. This problem can be formulated as linear programming problem. Let's denote or let's formulate the data. The x will be the x will be the number of units of the product A to produce. As you can see, here is the x, and y will be the number of units of the product B to produce here. As the objective function will be profit to maximize and using the formula of P equal to 3x plus 5y. Where it came from, it is because of the, if we talk about profit, it is in here. The product B is equal to 5, while the product A is equal to 3. And the constraints must be the use of machine, which is machine 1 is can be 2x plus y less than greater 8. Then machine 2 will be x plus 2y less than greater than 8. And the non-negativity is x then y is greater than equal 0. As we can see from this slide, we start for feasible solution, which is x minus 0 and y minus 0. The basis code is a variable of basic in each constraint. Then the RHS called the right hand I got right hand standard, and it's a right hand side of each constraint. That's what it's called. And the each row corresponds to a constraint for the objective function for to allow and each obtain the correspond to a variable. The process of the simplex method is to perform row operations to get a 1 in the pivot position, the variable to enter the basis, and zeros elsewhere in the column, the variable to leave the basis, and the update of RHS accordingly. This process is repeated until optimal solution is to found which is no negative coefficient in the last row for a maximization problem. As we can start, problem 1, we formulate the data as we initialization the data in order to in order to know where we should uh, pivot the data, and we choose the data where we can use the practical maximization. In step 1, we arrange the data where we can see the x is equal to x and y and x, which is here. X and y is equal to 2, while xx is 1, and xz is negative 3 because it is the profit, as you can remember from the problem. And y to y is 1, and y to x is 2, and its profit is negative 5 due to uh, as it's needed for the profit equal. And the right hand side is equal to 8. This is the corresponding hours of the machine 1 and also 2. Then in step 2, we can choose the variable with the largest coefficient in the objective function that can be increased while still satisfying the constraints. In this case, we choose y and increase it to 4. Then the new solution is x equal to 0, y equal to 4, and the profit is 20. As you can see here, where we increase x to 2, which is here, and equal to 26. And y, we choose y here, we increase it to 4, which is equal to 20. In step 3, we cannot increase the y any further without violating the constraints. We know to increase the x, and we can increase the x into 2 while satisfying the constraints. The new solution is x equal to 2 and y equal to 4, and the profit is 26. As you can see here, we did increase this we did increase this x to 2, which is equal to 26. In step 4, we cannot increase either the x or y any further without violating the constraints, so we have found the optimal solution. The optimal solution is what we used in the table. What can you see in the table, which is the 26 and the 20. So the company should produce 2 units of product A and 4 units of product B to maximize the profit, which will be the $26. So from the problem earlier, a company manufactures 2 products A and B. Each unit product A requires 2 hours of work on machine 1 and 1 hour for work on machine 2. Each unit of product B requires 1 hour of work on machine 1 and 2 hours of work on machine 2. Machine 1 is available for 8 hours a day, and the machine 2 is available for 8 hours a day as well. The profit on each unit product A is $3 only, and the profit of in each unit of product B is $5. The use the company wants to determine the number of units of each product to produce in order to maximize the profit. So we have solved the first problem earlier and its solution. As you can see, we have used the maximization with equality. So the company should produce 2 units of product A and 4 units of product B to maximize the profit will be $26. In example word number 2, where is a farmer has a field of 45 acres in which he plants potatoes and corn. Each acre of potatoes costs $200 for planting, requires 3 workers, and yields a profit of $500. Each acre of corn costs $300 for planting, requires for 2 workers, and yields a profit of $700. The farmer has $10,000 available for planting and 100 workers. He wants to determine how many acres of potatoes and corn to plant to maximize his profit. We need to formulate first or denote the data. X will be the number of acres of potato to plant, while Y will be the number of the acres of corn to plant, and the objective function will be P equal to 500x plus 702y. The constraints or the budget and workers are: budget is 200x plus 300y less than greater 1 I less than greater than 10,000. Workers is 3x plus 2y less than 100. Field size is x plus y less than 45. Non-negativity is y x and y greater than equal to 0. So our step 1 is to start with the feasible solution, which is x equal to 0 while y is equal to 0. The profit is p is equal to 0 also. As you can see here, all here is 0, which is our profit is in the bottom here. And as we see, x to x is 1, y to x is 0, y to x, another one is here, is 0, and y to y is 1. As you can see at the bottom will be its profit for negative 5, and our y equal to negative 700, and x is equal to negative 500. So we need to choose the variable with the largest coefficient in the objective function that can be increased while satisfying the constraints. In this case, we choose y and increase it to 20. The new solution is x equal to 0, y is equal to 20, and the profit is 14,000. So as we increase x to 15, as you can see here, we increase x to 15, which is equal to 21,500. And as we increase y to 20 here, which is equal to 14,000. Since we cannot increase y any further without violating the constraints, we now to try increase x. We can increase x to 15 while satisfying the constraints. The new solution is x equal to 15, y equal to 20, and the profit is 21,500. This is what I have explained earlier. We cannot increase either x or y any further without violating the constraints. So we have found the optimal solution. So the farmer should have planted 15 acres of potato and 20 acres of corn to maximize the profit, which will be 21,500. As our problem earlier, a farmer have field of 45 acres in which he plant potatoes and corn. Each acre of potatoes costs $200 for planting, requires 3 workers, and yields a profit of $500. Each acre of corn costs $300 for planting, requires 2 workers, and yields a profit of $700. The farmer has $10,000 available for planting and 100 workers. He wants to determine how many acres of potatoes and corn to plant to maximize his profit. So the farmer should have 15 acres of potatoes and 20 acres of corn to maximize the profit, which will be the $21,500. In example word number 3, a bakery makes two types of bread, whole grain and multigrain. Each whole grain bread requires 2 pounds of flour and 1 pound of grain yields a profit of $4. Each multigrain bread requires 1 pound of flour and 2 pounds of grain and yields a profit of $6. The bakery has 60 pounds of flour and 60 pounds of grain available. The bakery wants to determine how many of each type of bread to bake to maximize profit. And first, we need to formulate or denote the data. As you can see, X will be the number of whole grain breads to bake, and the Y will be the number of multigrain breads to bake. As our objective function, which is the profit to maximize, which is P is equal to X plus 6Y. The constraints are flour and grain, which is flour is 2x plus y less than equal to 60. Grain is x plus 2y less than equal to 60. Non-negativity is y and x and y greater than equal to 0. In step 1, as we always do, start with the feasible solution, x equal to 0, y equal to 0, the profit is equal to 0. As you can see there, right hand side is equal to 0 overall. And as you can see, x to y is equal to 1, and y to y equal to 0, x to x equal to 0, x to y equal to 1. So you can see negative 4 will be the profit, and negative y will be the negative 6. Negative 6 will be the profit of y, which is the multi-grain to make a bread. And the x will be the whole grain to make a bread. Choose the variable with the largest coefficient in the objective function that can be increased while satisfying the constraints. In this case, we choose y and increase it to 20. The new solution is x equal to 0 and y equal to 0, and the profit is p equal to 120. As you can see here, we raise x to 20, which is equal to 120. Since we cannot increase y any further without violating the constraints, we now try to increase x to 20 while satisfying the constraints. The new solution will be x equal to 20, y equal to 20, and the profit is 200. As you can see here, we raise the y, which is equal to 200. So we cannot increase either x or y any further without violating the constraints. So we have found the optimal solution, which is $200 from the solution we have made for increasing y from 20. So the bakery should have baked 20 whole grain breads and 20 multi-grain breads to maximize the profit, which will be $200. Our problem earlier will be a bakery makes two types of bread, whole grain and multigrain. Each whole grain bread requires 2 pounds of flour and 1 pound of grain and yields a profit of $4. Each multigrain bread requires 1 pound of flour and 2 pounds of grain and yields a profit of $6. The bakery has 60 pounds of flour and 60 pounds of grain available. The bakery wants to determine how many each type of bread to bake to maximize profit. In order to maximize the profit, we did the solution before the slide. So the bakery should bake 20 whole grain breads and 20 multi-grain breads to maximize the profit, which will be $200. In Simplex Maximization Method, where the quality uses the formulation of data. And that's all the video talks about. Thank you for listening and thank you for watching.